Hello my dudes, and welcome back to Viewfinder Engineering. Today we're going to be looking at some Bode plot basics. So before we get into the video, I just want to make y'all aware that this is a basic overview of Bode plots for first and second order systems. If you're looking for an in-depth analysis of sketching Bode plots by hand, then I'll direct you to my other Bode plot video, which I'll be linking in the description down below. So now that that's out of the way, let's talk Bode plots. Let's start off with some background. Bode plots show us how a system is going to respond to different input frequencies. If you think back to when we learned how to calculate gain and phase, you'll recall that we solved for both in terms of a generic frequency omega. When we plug in different numeric values for that input frequency omega, we find that our system output will have varying gains and phase shifts. So if we want to analyze a system's frequency response over a wide range of input frequencies, a Bode plot will allow us to see how our system will behave in each of those instances. Now, the important thing to note here is that while the system response to a constant input is a point on our Bode plot, the Bode plot is not the same thing as the plot of a step response. So like those graphs we have where a system reaches a steady state value when we analyze like rise time and settle time and all that kind of stuff, not the same as a Bode plot. Both graphs are useful, they just give us different information. Bode plots are all about mapping the particular solution over a variety of input frequencies. It's not about following one input with respect to time. Now, this all makes more sense when we start taking a look at these axes. Right off the bat, we can clearly see that this is not the standard position versus time graph that we've been working with up to this point. For starters, we've got this funky double x-axis thing, and our y-axis extends in both the positive and the negative directions. And this is really because the Bode plot is two plots in one. The double x-axes help denote that the top half of the graph is separate from the bottom half of the graph. So as opposed to like positive and negative, we have two different pieces to the y-axis here. On the top, we have gain, denoted G, and on the bottom, we have our phase shift, denoted phi. Now, these are both graphed against our input frequency omega, which is going to be our x-axis. But the tricky part here is that our Bode plot is graphed in semi-log scale. So, while the y-axis is a normal linear scale, our x-axis is going to be logarithmic, which means that each tick mark is an increase by a factor of 10. So, if we start with 10 to the 0, or 1, our next tick mark is going to be 10 to the 1, or 10, and so on and so forth. Now, like I mentioned a moment ago, the y-axis for both gain and phase is usually graphed in a linear scale. However, people like to be tricky sometimes, and there may be instances where you'll see gain graphed in the terms of decibels. Now, if you're like me when I started the course and you have literally no idea what a decibel is, it's just another funky logarithmic scale. And while we're not going to be using this when we draw Bode plots, Matlab does it, so it's just something to be aware of. So now that we know what these axes are, let's throw in a system and see what one of these things really looks like. We're going to be starting off with the first order system mv dot plus bv equals f naught sine omega t. And just for the sake of time, I'm going to go ahead and put this in terms of gain and phase. But if you need help with those calculations, I have a video for that too, which I'll link below, and you can watch it next. Now, let's start assembling our plot. We start out by looking at our DC gain, which is the system gain for a constant input. To find that, we take our gain equation and plug in 0 for omega. For this particular example, we find that our DC gain is 1 over b. On the gain half of our y-axis, we mark this value and then sketch out a horizontal asymptote. Now, the value of this asymptote will change at values that we call corner frequencies. These come from the poles and zeros of the system, but since we're just covering the basics today, all you need to know is that there will be a corner frequency at the magnitude of your system eigenvalues. Since this example is first order, we're just going to have one corner frequency. And for this specific case, we can find that the corner frequency is at B over M. We take our corner frequency and we write it on our x-axis. For first order systems, we know two things about our corner frequency. The first is that at this value, the slope of our asymptote will change from 0 to -1. The second is that at this point, the actual value for our gain will be 0.707 times the DC gain, or square root of 2 over 2 times the DC gain. We just use 0.707 as an approximation because it's a little bit easier than having to do square root of 2 over 2 every single time. But these two things are the same. Something to note here is that for any order system, the point where the gain changes by 0.707 is called our bandwidth. It just so happens that for first order systems, this point corresponds with our eigenvalue, which is super convenient. Finally, to finish drawing our gain, we just draw a line that follows our asymptotes. Next, we gotta draw in our phase shift. To start, we once again look at our DC value. For first order systems, when omega is 0, we know that there's going to be a phase shift of 0 degrees. And we can double check that by plugging in 0 for omega in our phase shift equation. So we do the same thing as we did with the gain. We start by labeling our phase shift for a constant input, which in this case will be 0. And then we draw out a horizontal asymptote until we hit our corner frequency. At this value, our phase shift will drop to -90 degrees. We can now draw in our line to follow our asymptotes, making sure that at the corner frequency, our phase shift has transitioned half of what it's supposed to. So since it drops to -90, we just need to make sure that at this point it passes through -45. Now, we can use this Bode plot knowledge to sort of work backwards in a sense. Given any input frequency, we can take to the Bode plot to find what the gain and the phase shift will be at that point. We can also use this to draw our system output and input on the same graph against time. Using the Bode plot, we can find the gain, which is going to be the ratio of the amplitudes, to know how the output peaks are going to look in relation to the input peaks. We can also use our phase shift to know how much of a lag there's going to be between the input and the output. Another handy thing is that we can use our Bode plot to find our system eigenvalue, since we know where the corner frequency is. Or we could even use the Bode plot to discuss whether or not two different responses could have come from the same system. Hint here, yes, I had to do all of these things on exams, and they would probably be good things to know. You know, the Bode plot is our friend. But I digress. Let's move on to second order systems. Now, second order overdamped systems are kind of sneaky because their Bode plots look really similar to the Bode plots for first order systems. However, we just have two eigenvalues now. The setup is all the same with the axes and stuff, we just now have to account for two corner frequencies. So we start the same way by extending our gain asymptote horizontally until we hit our first eigenvalue. And at our first corner frequency, our asymptote drops down to a slope of -1. Then we just kind of continue this logic, and at the second corner frequency, our asymptote slope drops down to -2. And the same pattern kind of holds for the phase. We start horizontal and then drop -90 at our first corner frequency, and then another -90 to -180 at our second corner frequency. So I'm not going to spend too much longer on this because it really kind of looks the same as our first order response, I just want to make sure that we're careful here. You know, when you see a slope of -2, think second order. And same with our phase shift. Even though it may look like first order if our eigenvalues are kind of close together, if you see a -180 degrees, you know that the system is second order, not first. So if you're, say, taking an exam and you have to discuss what order a system is based on its Bode plot, these are things that you will want to remember. Now, second order underdamped systems are a little bit trickier because now we have to deal with complex eigenvalues and this thing called resonance. I'll sketch out a generic graph really quickly and then we can use that to kind of discuss these two little hiccups. First, resonance. Resonance occurs when we have a small damping ratio. Even though our system is damped, for small zetas we will run into a frequency on our Bode plot where our system output is greater than our system input. If you will recall, our standard characteristic equation format for our second order underdamped system is s squared plus 2 zeta omega ns plus omega n squared equals 0. So, in this equation, it's going to be the second piece that affects resonance. For any value of zeta that is less than 0.707, resonance will occur. And the smaller the zeta, the more pronounced this peak is going to be. That's why we don't see resonance on our second order overdamped graphs. For overdamped systems, our zeta is greater than 1, which is also greater than 0.707. So the peak flattens out and just disappears. Now, just as an aside, also dependent on our zeta value is the slope of this transition in our phase shift graph right here. For larger zetas, this is going to be a more gradual transition. But for the extreme case of, say, like zeta equals 0, this is pretty much going to follow our asymptotes exactly, where our line is very sharp at the corner frequency. Our second hiccup here is the presence of complex eigenvalues. Now, remember, our corner frequencies occur at the magnitudes of our eigenvalues. But since complex eigenvalues have both real and imaginary components, when we take the magnitudes of our complex pair, we find that both magnitudes yield the same value. You know, we basically have two corner frequencies right on top of each other here. And we have to take this into account when drawing our asymptotes. So now you'll see that our slope drops by -2 instead of by -1. And similarly, our phase shift doesn't drop by 90 and then to 180, it just goes straight from 0 to 180 at our singular corner frequency. Now, those were our two new hiccups, but we still aren't done, because we still haven't completely defined this Bode plot. Now we need to look at the formulas for all of these terms we just introduced. And to do so, I'm going to make a table. I just find that tabulating these formulas makes them easier for me to remember and easier to put on a formula sheet, but you know, you do you, these all are separate things and they can exist in their own little spheres. First, let's start out with the DC gain. We already established earlier that this is the gain for a constant input. We'll denote it as GDC on our Bode plot, and its gain is system dependent. We find it by plugging in omega equals 0 into our gain equation. Next, we have the corner frequency, which is also called the natural frequency. It's denoted by omega n and occurs at the omega n defined by our magic characteristic equation we looked at earlier. The gain here will be the DC gain times 1/2 zeta, and here there's one last thing to note. For the special case where zeta equals 0.707, our natural frequency will also be our bandwidth. Now we need to talk about resonant frequency, which we will denote omega r. It occurs at a frequency of omega n times the square root of 1 minus 2 zeta squared. The gain at our resonant frequency is the DC gain times 1/2 zeta times the square root of 1/1 minus zeta squared. Truly a mouthful, but it's easier to write than to say. And it is important to note here that we will only have resonant frequencies if we have resonance. So in order to have this, our zeta has to be less than 0.707. Finally, we have our bandwidth, which is denoted omega BW. The frequency it occurs at will be zeta dependent, but the gain value will always be 0.707 times the DC gain. So there you have it. Bears beats Bode plot basics. Hopefully this helped shed some light on how to read Bode plots and on how to set them up for first and second order systems. Thank you so much for watching. Be sure to hit that like button if this video helped, and to hit that subscribe button if you want to see more college level math and engineering and science content. Okay, bye.